So welcome to this class. In the last session we just briefly described about the sputtering process. So we talked about the sputtering process is nothing but a removal of atoms from the surface from the surface of the sample, and the conditions for that these surface atoms has to get enough energy, and the atoms has to be displaced outside the sample, and we described this as a 4 conditions. One as the ion beam should have enough energy, the initial ion beam energy. Okay, so and it also depends upon the surface, the binding energy, energy of the surface atoms, and the third is the incident angle, okay, which is a very important parameter, which is an important setting where you can actually increase the sputtering process. You can increase the rate of sputtering process, or we can call it as a sputtering yield. Okay, so the sputtering yield is described by how many sample atoms are sputtered per incident ion. Okay, so for a gallium ions, the FIBs where you use the gallium ion source, this particular yield is between 1 to 10 for an ion beam, where when the beam interacts with the sample surface perpendicular or 0 degree tilt for the sample, correct? So this is particularly about 1 to 10. So yield can be defined as the number of sputtered atoms divided by the number of incident ions. Okay, so here we talked about this particular incident angle. Okay, so this is a very important parameter, which can control your the sputtering yield, correct? So if you have a sample surface, if your beam falls exactly perpendicular to the sample surface, your ion beam, then usually it is called as a incident angle of 0 degrees, correct? Now if in case if you make your either tilt your, so you have a sample surface, either you can make tilt your ion beam, or you can make the sample tilt, so that in such a that the ion beam is not perpendicular to the sample surface, then your sputtering yield increases significantly. Okay, so based on the experiment, usually what we tell is if you have this sputtering yield and this is your incident angle. Okay, so sputtering yield, it is nothing but, as I told you, the number of ions removed per ion. Okay, so if this is a scale of 30, 20, 10. Okay, so as your angle increases from 0 to 90 degrees, so your sputtering yield also increases, and it reaches a maximum at a certain angle, which is between 70 to 80 degrees, where your yield is much higher, correct? This is your dependence of incident angle, of the ion beam with respect to your sample surface. Okay, and this sputtering yield also depends upon your accelerating voltage. So your yield, your accelerating voltage, then your yield increases with your accelerating voltage from 5 kV to 50 kV. Or 5 or 2 kV. Okay, so your yield increases with the accelerating voltage. So this is a typical curve of the variation of the yield with respect to your accelerating voltage. Right. So with this, what we briefly has gone through is your ion column. Okay, your ion column. Then we just talked about the source, which is usually a gallium plus ion source. Then you will have a condenser system or condenser lens. You will have an aperture of condenser where you can actually control the beam current. Correct. If you want a very higher sputtering yield, then your beam current also should be increased. And if you want to more increase, then you can actually play with the incident angle of the sample surface with respect to the ion beam current. Okay. Here you have an objective lens, which usually it focuses, and you have some set of lenses, octopole or quadrupole, which actually controls the scanning of the beam and also the aberrations of the beam. Correct. And you have a blanking plates. So whenever you don't want sputtering to be happened, actually then we can put the blanking plates which blocks the ion beam against the interaction of the sample surface. Correct. So this is a typically interaction of what we discussed about is the ion beam versus interaction with your sample surface, and we basically only talked about the sputtering process. Now the next, when we discussed about in the in 2 classes before, then what we shown is you have a electron beam column. Okay, this is your chamber, this is your ion column, and there is one more column which we call it as a gas injection system. Okay, gas injection system. This is a very important part of the FIB, which is for operation of FIB. Okay, so what is the gas injection system? So we will just briefly go through the gas injectors. What are these gas injectors? Okay, now this gas, so if you have a sample surface here, okay, and your ion beam falls on the sample surface, this is your gallium plus ions. Gas injection system is nothing but a precursor. It has a precursor. Okay, so why these precursors? So these gas injectors or the gas injection system, we call it as a GIS. It usually introduces reactive neutral gases onto the sample surface. Okay, so you have a sample surface. This is your gas injection system, and it is just kept just above the sample surface. It is kept around 200 micrometer distance from the sample surface. Okay, and you have an ion beam coming from the ion source on the sample surface. Correct. And this gas injection system, it is nothing but it induces these reactive neutral gases onto the sample surface, and these neutral gases can do etching or preferential etching, or also it can be used as a metal deposition. Okay, so GIS system, it is nothing but a controlled flow of gas from the crucible. This is your crucible, which contains GIS precursor. We call it as a precursor on the sample surface through a nozzle. So this is called nozzle. Okay, so these precursors usually solid, correct, and we need gas. So usually these GIS needles, so these precursors are heated prior to the injection. Okay, so due to the heating, this converts to a gas, and this gas is injected onto the sample surface. Okay, and the gallium ions which are accelerated toward the sample surface, they can interact with this gas and they can decompose the precursor. How? These gallium ions can interact with the precursor gas, these gallium ions, and they can decompose these precursors. And during decompose or cracking, you can call it as a decomposition or cracking, then these precursors which is having a certain metal, that metal gets deposited onto the sample surface. Okay, so based on the metal which is contained in the precursor, it can be platinum rich, it can be tungsten rich, it can be carbon based, carbon rich, based on the metal which you want to deposit on the sample surface. Okay, so you can use different types of precursors which we call as a GIS needles, where you can actually use a precursor which is a platinum rich, tungsten rich, or the carbon rich, and when the gallium ions interact with these platinum rich, tungsten rich, or carbon rich precursors, these precursors usually crack or decompose, and the platinum or the tungsten or the carbon gets deposited on the sample region wherever the gallium plus ions are going to interact with the sample, correct. And these gaseous precursors are nothing but they have a chemical compound as 3, either it is platinum CpCH3. Okay, so this particular precursor get cracked by the ion beam, by the interaction of the ion beam, and these metals, whatever the metals you want to deposit on the sample surface, gets deposited. So this is the role of gas injection system. Okay, and then the gas injection system, what is the use of gas injection system? One is, I told you, it is for the etching, for a deposition, and also for the welding. Okay, welding. So we'll come to the welding later stage. First we'll describe the another part of the FIB system, which is called manipulator. This also is a very important function in the, so again I can draw you, this is an electron beam column, you have a chamber, fine, then you have a ion source, you have a gas injection source, gas injection needle, correct. So and you have a sample surface. Now there is another system which we call it as a manipulator. Okay, manipulator, it is nothing but a sharp needle which is used for lift out or removal of sample surface, removal of any region from the sample surface. This is used for the lift out procedure. Okay, so lift out procedure means from the lift out, either you can lift out the TEM lamella or APT lamella. or any region which is your which is important for your investigation, this manipulator can be used for the lift out procedures. Correct? So there are three important things in the FIB system. One is the ion source, the second one is the gas injection system, and the third one is the manipulator. By combined usage of three important components, actually you can prepare the sample surface and you can remove the region of interest from one place of the sample surface and you can paste into the grids, and these grids can go for the inside the TM or inside the atom probe tomography. Correct? So these are the manipulators, sharp needles. Fine. So basically you have a electron beam, you have a ion beam column, electron beam column, you have a gas injection system, and also you will have a manipulator. First, second and third. Correct? By using these three on the sample surface, you can actually remove the region of interest and paste into the grids. Fine. So I will briefly show you a video where you can understand how a sample is prepared, especially for the atom probe needles. Okay. So this is a courtesy from Max Planck. So here you can see so here you can see the sequence. So here there is a grain boundary. You are actually sputtering out this particular region, sputtering out this region. So this is your grain boundary, correct? And you are removing these two regions by using the gallium ion source. Fine. Now once, and you can see that the one end of it got cut from the gallium ion source, which is independent of the sample. Then you use this manipulator and you use the gas injection system to paste or weld the sample to the manipulator, and this particular sample is then pasted on a silicon coupon. Okay, and this particular sample with the grain boundary is again we use the gallium plus ions for making a atom probe needle specimen. Fine. So here you can see that the importance of the three important parts of this particular. So one is sputtering by the gallium ion source, correct? Another one is the gas injection system and the manipulator. Okay. So by using the manipulator, you can actually lift out this particular lamellar, correct? So this is your manipulator. You use gas injection system to deposit the platinum, and it gets deposited and it gets welded. Then you are lifting out the lamellar and pasting on the silicon post, and subsequently it got milled, and by keeping the area of interest, which is a grain boundary, for the field evaporation in the atom probe. Correct? So I hope that you understand the role of now focused ion beam. Okay. Now, so by using these ion beams, as I told you, in any material you can actually deposit platinum or carbon, okay, on the sample surface. So actually if you have a certain region of interest, then actually you can mark that particular region by the platinum deposit or tungsten deposition on the region of interest. Okay, then you can do the cross section. Then also you can mill the sample in such a way that you can extract the different shape of the specimens, either cylindrical rod, either you have a lamellar, okay, based on the requirement. Okay, so this particular usage we call it as a patterning mechanism. You can use different patterns on the sample surface by using the gas assisted injection system or gas assisted deposition. One more important application for this particular is the 3D reconstruction. 3D reconstruction. Now if you have some sample surface, okay, so now if you have a certain region, and you have a certain grain boundary at the cross section, and you want to see this grain boundary evolution in 3 dimensions, correct, in 3 dimension in this direction. So you need to slice out each layer by layer, first layer, second layer, third layer, fourth layer. So you can use this ion source or the gallium ion source to remove this material sequentially, and you can take cross section image by using the electron beam, and you can stitch it to see the 3D reconstruction of that particular grain boundary or the grain. Okay, and one more important thing, if you have a EBSD attachment, then actually you can do the EBSD on this particular surface, and you can remove this surface, again you can do the EBSD on the second surface, and these EBSD patterns can be stacked together to get the 3D EBSD data. Okay, so this is how you can use this ion source. It's a powerful tool where you can actually do the 3D reconstruction or 3D tomography. We can call it a 3D reconstruction, either the EBSD maps or the grain orientation maps, or also the imaging 3D reconstruction of the features which are inside the surface. So this is your top surface, this is your bottom. Okay, so by using the FIB, actually we can do the 3D reconstruction in 3-dimensional construction. So needless to say, the beam which is falling on the sample surface, it directly also depends upon your accelerating voltage. Okay, as in the electron microscopes, you have an interaction volume based on the voltage, correct? As your voltage decreases, your interaction volume also reduces. This is your sample surface. So this is your electron interaction volume. Similarly, for the gallium FIB also, you can actually, the interaction volume for 30 kV will be much higher, for 20 kV it will be less, for 5 kV it will be much less. Okay, so based on that, so this is the interaction volume. It is nothing but the travel path of the gallium ions until it loses all its energy and it's get deposited. Okay, so based on the accelerating voltage, you can have a different interaction volumes. And as I told you, the ion implantation, which is a major artifact, ion implantation, that may change the composition or structure of the sample surface. So higher is the accelerating voltage, the interaction of these gallium ions with the sample will be much higher, then ion implantation also will be rate also will be much higher. Okay, so based on your applications or based on the sample or atomic number of the sample, you can actually use a proper choice or the optimum choice of the accelerating voltage for this, correct? So this ion beam, as I told you, in the ion column, we have a octopoles and quadrupoles, correct? And by using these two set of poles, actually you can scan the beam on the sample surface. So if you have a sample region, actually you can scan the beam into the left to right and right to left and the left to right, top in XY direction. You can scan the beam as per your need by using the combination of these octopoles or the quadrupoles. Okay, so this is how we can scan the beam. So actually then you can use the patterning, a required patterning on the sample surface, correct? Okay, now as in the electron beam case, the electron beam should be sharp enough as a point source, correct, in SEM or in TEM, okay, and they also have certain aberrations in an electron microscope. Similar aberrations also exist in the ion source, okay. So your ion beam alignments are very crucial, correct. If your ion beam alignments are not proper, then you may not get a proper patterning, okay. Even though you have kept a pattern for the rectangular section, but due to the aberration in the beam, okay, so due to that aberration, it might possible that you can not get the sharp rectangular cut or the sharp rectangular sputtering. You may end up with a bulged, okay, due to the aberrations, okay. So the first important point is the beam should be focused on the sample. If it is a defocused beam, you may induce that very unsharp edges. So if you want to a rectangular cross section or like rectangular cross section sputtering process, these edges will not be sharp. It might be bulged due to the unfocused ion beam, okay. If you have a stigmated beam, astigmatism, okay, this also is a very important because it also has electrostatic lenses due to which the astigmatism may form. So your beam is not focused, correct, and due to astigmatism you may get the distorted sputtering of that particular pattern or the shape, okay. And both these two can also be exist in at a time, which can lead to a very distorted milling. We can call it as a milling or the sputtering process, and you will not get the exact morphology of the specimen what you need. Fine. So with this, so what we have described now is the sample preparation by focused ion beam, correct. It can be also used as a focused ion beam microscopy, FIB, okay. And we have described the basic cross section of the column, what are the important lenses. So we call it as a electrostatic lenses. I explained you that why electrostatic lenses are used, not electromagnetic lenses. That is due to the ions, not as electrons in SEM or TEM, correct. It will have a better control of the ions because ions are heavy, their velocity is very low as compared to the electrons which are fast moving, and electromagnetic lenses, the force on those electrons are proportional to the velocity of the electron, but here the velocity is very less, so you need very large magnetic lenses, okay. So due to which you use the electrostatic lenses, and electrostatic lenses, they don't have dependence on the velocity of the charge, okay. So that's why we use the electrostatic lenses, okay. So now these ions get accelerated, they can actually use for the patterning, they can use for the sputtering process, they have a certain projection depth, okay, which is the interaction of the gallium fib inside the sample until it loses all the energy. We also talked about this is your ion source. So ion source is only for the sputtering process. The second important thing is the gas injection system. Gas injection system, which we call as a GIS. These are nothing but the precursors, chemical precursors, okay, which has a certain element like platinum, tungsten or carbon, and these precursors are decomposed or cracked when these precursors interact with the ion beam, due to which it can deposit on the sample surface, correct? Now if you want to remove your material or the region of interest from the sample surface, you have to use the manipulator. And this gas injection system can also be used to weld the lamellar or the region of interest to the manipulator. And this manipulator again can be used to transfer your region of interest onto the TEM grids or APT sample holders, which is nothing but a silicon posts, or silicon coupons. We'll have a silicon posts, correct? So this will briefly, I will go through it in the later stage when we talk about the correlative microscopy. Fine. So I hope you got the clear picture of this most used sample preparation method nowadays is FIB. Okay. So in FIB you use gallium source. So nowadays this gallium, as I told you, with certain elements, the gallium can actually interact with those elements and can form compounds which are detrimental or which acts as a artifacts. Sometimes gallium implantation also gets to the fracture of samples, brittle fracture of samples during field evaporation. Okay, so this is due to the interaction of gallium to those elements. The most high rate in interactive element is aluminum or the light aluminum. It forms, it contaminates the aluminum, especially if it is a nanocrystalline form. So gallium diffusion along the grain boundaries is at a much higher rate in the aluminum case. In some cases with magnesium alloys, it can form certain compounds, magnesium gallium based compounds, which are actually artifacts into the sample in the TM sample preparation, correct? So nowadays there is depending upon the source, we also have a xenon plasma FIBs which are almost inert as compared to the gallium, and these xenon plasma FIB, these xenon sources, usually they don't react with the elements because of their inert nature. So these plasma FIBs are now coming up, and instead of gallium plus ions, you use the xenon plus ions. Okay. So another method is the low temperature milling, cryo temperature. We can call it as a cryo temperature. So usually the milling in FIB we do in a very high vacuum atmosphere at near about room temperature, and the diffusion of gallium into the sample at room temperature will be much higher, because these are the liquid gallium plus ions, and diffusion at room temperature is much higher into the sample surface. If you do the cryo milling, temperature milling, then the diffusion of gallium plus ions can be limited. So you can reduce the gallium damage on the or especially on the aluminum samples or the magnesium samples if you do the milling in a cryo temperature, means liquid nitrogen temperature. So there are certain cryo holders or cryo setup are available now, where we can install these cryo setups and we can do the low temperature milling to reduce the gallium damage or to prevent the gallium damage from the sample surface. Okay, and this cryo setup also gives an opportunity that these ion mills can be used for the biological samples, sectioning of biological samples or polymer samples. Okay, so these are the different accessories which can add on to the existing gallium source FIBs, where we can reduce the damage caused by the ion beams, and it can be used for the biological samples or the polymeric samples at liquid by low temperature milling. Fine. So I will end this class now. So now we have completed the sample preparation methods. In two class before, I just briefly described about the electropolishing, which is also now also it is being used, but only problem is electropolishing. The site specific samples are very difficult to prepare. Okay, so so if your sample is homogeneous, and if your sample has a precipitates or phases which are distributed uniformly along the microstructure, then the electropolishing can be used effectively. But if you need a site specific samples, for example a particular phase, particular interface, grain boundaries, twin boundaries or faults, then actually you need to prepare the sample by the site specific. Okay, so more on the sample preparation methods in FIB we'll just briefly go through in the next class, where we have a different lift out methods. Okay, so as I told you, your ion beam falls on the sample surface. You are actually milling the sample, just the cross section samples you are making it. Actually what we can do is we can also do the in plane lift out methods. So now if you have a sample surface, you know this is a particular boundary, but if you see the cross section, you don't know this boundary can go inside the sample or it just comes out. We don't know the whether the boundary exists or not. So what we can do is we can prepare a sample which is in plane from the sample surface, and we can make sure that in the needle specimen, whatever you are making the needle specimen, you have that particular boundary perpendicular to the axis, the tip axis, correct? So these are different in plane lift out methods which we'll go through briefly in the next class. So we'll meet in the next class with these furthermore descriptions. Thank you.